Okay, so welcome to Lecture 5, Part 1 for the Real-Time Digital Signal Processing Lab class at the University of Texas at Austin. Any questions from previous lectures? Comments? Okay, so today's the first lecture where we get into some live demos, and we're doing live demos almost every day for the next 3 weeks or so. Today the live demo will be in Java, but future demos are in MATLAB and also on the web. So if you want to bring your laptop, it's also fine for running the demos alongside of what I do up here on the desktop. Okay, so the topic is finite impulse response filters. This will be homework 2 and 3 and lab 3, and also labs 5, 6, and 7. So this is a basic building block. It's of all the building blocks we cover for discrete time systems, this is the most common one in a signal processing system. So this is the one to learn really well. And the other major building block is infinite impulse response filters. And the third major building block is sinusoidal generators. Fourth one is pseudo noise. We'll do all those. And the fifth one's FFT. That's also very important. So those 5 together, the fast Fourier transform, form kind of what we do in signal processing. It's a bulk of what we do. So it's analysis in both the time domain and the frequency domain. All right, so this is actually a 4-part lecture. So today we'll do the many roles of filters and review convolution, and we'll cover the other topics in the other parts for lecture 5. Okay, so now I get the little philosophy. I don't do this very often in lecture, so we'll talk about the philosophy of filtering, if you will. And I remember a couple years ago, a student in this class asked, are we going to do filtering? And I said, yeah, about half the class is filtering in one form or another. And you've seen this already with sinusoidal generation. We use difference equations, which is a filter, to generate a sinusoid. Okay, so many roles for filters. So then we give you 3 different large uses or big picture uses of filtering. And this is true for whether it's a finite impulse response filter or infinite impulse response filter. So the first one is just noise removal. We know we have noise. We at least have thermal noise. Sometimes we call that background noise in our system, and that noise is pervasive at all frequencies. Mathematically, we model that as noise being equally present at all frequencies, but in practice, it's not equally present, but it's pretty close to being a flat power spectrum over frequency. So for the purpose of noise removal, we're going to need to have the signal and the noise spectrally separated. Now, what this really means is that for the noise that is occurring at frequencies outside of our band of interest, we can filter those out or at least attenuate those, reduce their strength. So an example of that, if I do bandpass transmission in a communication system, or a bandpass signal in general, could be an audio signal, I could bandpass filter to suppress out-of-band noise. This will improve what measure of signal quality do you think this will improve? SNR. So what we do is we pass the signal that we want. So we put the signal frequencies, the signal of interest, we'll pass those frequencies and then attenuate the other frequencies where the noise resides. Now there will be some noise, unfortunately, in the same band as our signal, and we can't filter that out using this approach, but we can at least filter out the noise that's outside of the band of interest. If our signal were low frequency, so it's an example, an image would be an example of that. Video sequence would be an example of that. So if I have a low-pass signal, then I can apply a low-pass filter to remove high-frequency noise. Averaging filter is an example of that. Okay, so we'll look at this on homework, I think homework 3. We'll look at this issue quantitatively. The second big picture use of filters is analysis, synthesis, and compression, and in particular spectral analysis. Now we've done spectral analysis manually by taking the Fourier transform. We've also done it by MATLAB by using plot-spec, and plot-spec underneath applies a Fourier transform, a fast Fourier transform, to the sampled signal to create the frequency domain plot for us. So we've been doing spectral analysis. And it turns out that the fast Fourier transform, and we'll talk about this at some point, can be thought of as a filtering operation. All right, but let's we'll leave that aside for now. And so we'll hear a couple of examples of analysis, synthesis, and compression using bandpass, low-pass, and high-pass filters. So one thing we can do is we can actually use a bank of filters, a bunch of filters in parallel, tuned to different frequency bands to calculate power spectra. And in some sense, that's what the fast Fourier transform actually does. Another example that we'll see later is a very efficient implementation of a thing called pulse shaping. So in pulse shaping, what we're going to do is take a discrete-time digital message and get it ready for transmission through a continuous-time analog media. And one of the steps in that is called pulse shaping, which is really FIR filtering, or finite impulse response filtering. And this will determine the transmission band that we end up using in transmission. There is an efficient implementation for this, which is called a polyphase filter bank. So this is a parallel combination of filters, and it has less complexity than a direct implementation. We'll get to all this after spring break. But this is another example of this would be analysis on the transmit side. I have to be careful which way I go with this. So we're going to use this polyphase filter bank at both the transmitter side for pulse shaping, and the dual of this is called match filtering on the receiver side. Go ahead.
Is the purpose of this pulse shaping like to force the signal to a certain region in order to be able to transmit? Maybe if there's other signals kind of existing in the same band.
Yeah, that's right. So the question was, what is the pulse shaping's role to put the signal that we're going to transmit in a certain band of frequencies? The answer is yes. So we'll start, this will be a low-pass filter, and then we'll follow that with up conversion to make it a bandpass transmission. So multiplied by cosine to shift the center of the baseband to the new frequency, the new carrier frequency. Okay. So we'll do this both on the transmitter side and the receiver side. Okay. So anyway, so this is a way of basically, I can think of this as a way to synthesize a new signal from an existing one. Now, I don't have a compression example listed here explicitly, but compression, the idea in compression, this is true in image compression in video and also in speech and audio compression, that there are certain frequencies that are not important as others. We may not hear it very well. Example of this, if I have in audio, if I have a tone that's really, really high in volume next to another tone really low in volume that's right next to it in frequency, I don't hear the low volume tone. The high volume tone nearby masks out the low volume tone. So we can just filter out the low volume tone. We don't have to encode that. Also, what's interesting in compression is that both our auditory system and our visual system is roughly low pass. So in the case of audio, it's low pass in frequency. And again, we hear out to about 20 kilohertz. For visual, it's low pass in both spatial frequencies and in temporal frequencies. So frames would be time in a video sequence, and each frame would be a capture, a snapshot of space. In both cases, our visual system is low pass. So we can compress a signal simply by not encoding, at least very many bits anyway, high frequency information. It's not as important as the low frequency information to our human visual system. So we can use filtering to aid compression, and we do in practice in standards. This is in JPEG, for example. It's an MPEG. Third big picture is spectral shaping. This is the idea that if I have a spectrum and I'd rather have another spectral shape, I can use filtering to change it. Right. So a good example of this, let me do a very simple example. Let's say I'm stuck with noise. So let's see if a good example. Okay, so channel equalization is a good example. So in a communication receiver, if my communication channel, let's say, is low pass, or just for an example, just for bandpass transmission, this would happen in DSL or wireline communications. We may not, on the receiver side, what we'd like to be able to do is make sure that the transmitted signal got through, and whatever frequencies we're using in the transmitted waveform, we would like the receiver to compensate any distortion that happens in the channel. So the channel can be thought of as a filter. It could be low pass, high pass, bandpass. And the receiver is going to have its own filter to compensate. So if I have a low-pass channel, my equalizer would be high-pass. If I want to equalize overall frequencies. Audio systems do this, right? If I want, so in audio, we tend to break up a audio signal into subwoofer, woofer, and tweeter frequencies. So very low is a subwoofer, then woofer, then tweeter. And these are basically bandpass filters. And if I want to turn up the subwoofer, I can take the audio signal, decompose into these three bands, and put a gain on the subwoofer part, and then combine them back together and send them out. So channel equalization is the idea that I want to change the relative strengths in different frequency bands of what the signal I get. So in the communication system, it's the receiver doing this. Go ahead.
What is the difference between spectral shaping and pulse shaping? I feel like they're both the same thing.
Yeah, so the pulse shaping is going to take the pulse shaping can be thought of as spectral shaping because it is a low, so all these could be low-pass filtering but have different uses. So again, this is to remove out-of-band noise if it were a low-pass filter, remove or suppress high-frequency noise. The pulse shaping is to limit the transmission. Instead of using all the way out to half the sampling rate, we're going to use a smaller amount of frequencies. The equalizer, if I have a high-pass channel, the equalizer would be a low-pass filter. So there's still a low-pass filter can be used in each of these three.
The spectral shaping is more like, it's kind of like you want to selectively remove certain frequencies. Pulse shaping is you only want to keep a certain band range frequencies.
You could, yes, and in particular, the way that we're going to implement the pulse shaping is really the connection. So what analysis will, so I'll give you a very simple analysis example. So I take a signal, x of n, and I pass it through a low-pass filter and a high-pass filter. I now have two signals, x0 and x of n. Okay, so this is analysis. I've broken up a signal into two components. A low-pass, I've broken it up into its frequency components. The low-pass filter could be what? What's an example of a low-pass filter you've seen already? Averaging filter, two-tap FIR filter, very simple to implement. So the impulse response of h of n, I don't have to have it normalized. I don't have to use normalized. So there's your impulse response, right? It just takes, so in terms of input-output relationship, it's going to average the current input and the previous input value. High-pass filter, what's an example of a high-pass filter?
Differentiator?
First order, a differentiator, first order, the equivalent of first order difference, or first order differentiation, which we would call first order difference. What's that impulse response look like? Yeah, delta n minus delta n minus 1. Okay. Now there's and we could certainly scale by a half to make it normalized in both cases. I'm giving you the unnormalized version. So that's the analysis side, is to break it up into high frequency and low frequency and high frequency components. So the way that we're going to implement the pulse shaping, you're right, the pulse shaping can be thought as spectral shaping. The way we're going to implement it, though, later on, is as a bank of filters, and each filter is basically tuned to a different band. So I'm going to take a signal that comes in, and I'm going to break it up into these particular bands, and each signal is going to be interleaved and put onto the output. So the way that I implement it is as an analysis, as a bank of filters doing analysis for me in this form. So that's analysis. Synthesis, so this is analysis. Synthesis is the dual of this. Synthesis would be, given these two components, low pass and high pass, how do I now recombine them to get back to x of n, or at least as close as I can to x of n? So how am I, so now my inputs are going to be, for synthesis, I have x0 and x1. Now, The more general way to do this is to have another bank of filters. It turns out in this case I could actually avoid the filtering, but I'll give you the general idea is that I'm going to reinforce the band of interest. So x of x naught is low pass already. And I'm going to add them together to reconstruct x. Now, I also have a gain that I have to worry about here. There's a gain that what I'm going to get out of here, if I use the same low-pass filter, so I use, again, the averaging filter. So my low-pass filtering is an averaging filter. My high-pass filter is a first-order difference. So the synthesis will use the same filters again. Now I can combine them to get an estimate of x of n. And what I end up getting, because I did normalize, I'm going to get, I think I get 4xn in this case. So the synthesis, what it will do is, again, take these components of x of n, x0 and x1 of n, combine them in a way to get back to an estimate of x. Now, the two things happen. There's a gain that happens, because I didn't use normalized filters. And second, there's a delay. There's a delay through each filter to the output. Now, it's a little early to tell you this, but the delay through each filter is a half sample. And so the delay from x of n to its reconstruction is, what's the total delay through the analysis and synthesis banks? It was 1. So delay through this filter is a half, delay through this filter is a half. The total delay is 1 sample. So n naught is 1 here.
So why do you filter x naught and x1 before summing them together?
Well, this is the general approach, and this would handle things like there's noise, or I do some additional filtering between here and here. If I didn't alter x naught or x1, all I'd have to do is add them together. And you can see that, because if I add them together and I add the impulses together, these two terms subtract out. I'm just left with the impulse. I'm left with an identity system.
Are those supposed to be the same? One of them's n plus 1.
Oh, it should be n minus 1. Thank you. N minus 1. Causal. So I do something non-causal, let me know soon. Thank you for letting me know. Okay, so we'll spend a lot. The spectral shaping is these topics are going to be after spring break. They're going to come up later in detail. In terms of compression, what can happen is if we can break up the signal into these frequency bands, then we can assign a different number of bits for each band based on their relevance to how they'll be used. So if we're going to view an image or hear audio, then we put as many bits into each bin as our human system would respond to that band of frequency. So in audio, for example, we have a sweet spot. In audio, for example, we have a sweet spot right around 1 kilohertz. That's where we hear the best, our strongest response. So for the band that would contain 1 kilohertz in an audio analysis that we use for compression, we want to put more bits in the 1 kilohertz band. And as we go to higher frequencies, we don't have to use as many bits to encode that band. We don't have as much response in our human auditory system. So that's the idea of one idea of compression. So filtering is pretty useful in general for lots of applications. So here's the finite. So that the previous slide is true for both finite impulse response and infinite impulse response filters. So let's talk about FIR filters. We've seen this already. This is the finite impulse response filter is the same as a discrete time tap delay line. And so the delay elements are along this delay line. I've drawn it horizontally. It's okay if I draw it vertically later. We'll do it different ways. So here I've got the delay line horizontally. I've got capital M-1 delays. The impulse response you can read directly off of the block diagram. This time I've more explicitly denoted the impulse response. It also tells you that the impulse response has finite extent. Go ahead.
I have a little trouble understanding what you mean when you say that all of the like coefficient terms give you like the impulse response. Can you like elaborate on that?
Sure will. So let's see what's an example. So let's take an averaging filter. Okay. So and we'll do the normalized one. Okay, so for a normalized averaging filter, we can draw the same block diagram because we know that the input output. So for an averaging filter, I average the current input value with the input one sample ago.
Okay, yeah.
Okay, so that I can write as a tap delay line. So first of all, what's the impulse response? The impulse, this is averaging filter. Okay, so what's the impulse response? Right, so we just let x of n be the impulse, discrete time impulse. And so the impulse response right. Now we can write this as a tap delay line or express it in a block diagram. What is H naught? Well, H naught is just a coefficient. H naught is 1/2. That's H naught.
Oh.
And what's H1?
Oh, it's 1/2.
1/2. And that's this one. So this averaging filter is a finite impulse response filter, and I can represent it as a tap delay line with one delay element, two coefficients. And the coefficients are 1/2 and 1/2. Now, I can also see why it's an impulse response by just writing out the input-output relationship, which we didn't do last time at the end of lecture 3 slides. So we can do it here. So I want to look at, I want to follow the input to the output. All right, so here's the first path. Mildly not visible, back row. Not visible. All right, so we're going to take the first path from input to output. That's just y of n is x of n times x naught, h naught. Let's see where I'm going to write this. Next path through. Right, so I delay by 1, I get x of n minus 1. So I get x of n minus 1 times h1. And then the final term, x of capital M minus 1 times x of n minus capital M minus 1. Right, there's my difference equation if you want, although it doesn't involve any differences with the output signal. All right, so if you collapse this down into a summation, and I use a placeholder variable of summation, this little m, all right, so when little m is 0, I get the first term, little m is 1, I get the second term, and then finally when little m is capital M minus 1, I get the last term. And this should look really familiar. Or I hope it looks really familiar. And if not, it will become really familiar. Right? This is nothing but convolution. This is the convolution of the impulse response of the LTI system, H of M, and the input signal X. Now, it's interesting that this block diagram implements discrete time convolution. And the way it does it is kind of interesting. If you look at what happens along the delay line, I get x of n minus 1. After the next delay, it's x of n minus 2. And finally, the last output is x of n minus the quantity capital M minus 1. So this delay line, so when you think of convolution, we have thought about it in signals and systems, and we will think about it again this way, that we hold a signal in place, like H, the impulse response, and we flip and slide the input signal across the impulse response. Right? The flip is because of the minus M, and the slide is because of little n. Little n is the outer variable in the convolution. Well, it turns out the flip and slide is actually implemented by the delay line. So what's kind of nice about discrete time systems is that the discrete time convolution formula has a direct implementation as a filter in the time domain. I don't have to go to any other domain. I don't have to go to the Z domain and back to find a useful implementation of the discrete time convolution formula. Pretty cool. Continuous time, it just isn't this simple. I have to go to the Laplace domain. I have to look at where poles and zeros are. I have to then map that to a circuit topology from the Laplace domain. It's quite involved. All right. So it's pretty cool. Very useful structure for us. So again, this is just extremely common. You will see FIR filters in any, I can't say every, but I have to say it's very common in any system that processes signals. Speech, audio, image, video, communication systems, biomedical instrumentation. This is incredibly common structure. The most common one that we'll do in an embedded, certainly in an embedded system, this is the most common structure that shows up. There are other common structures, as I mentioned, IR filters, pseudo-noise generation, FFT, sinusoidal generation. This is just extraordinarily common. All right, so what can you do? So when you design an FIR filter, you get to pick the number of coefficients, and you can do this on a couple of cases manually. So if you need a really simple averaging, a low-pass filter, you can use the averaging filter. If you want a simple high-pass filter, what would you do? First order difference. And for a first order difference, H of 0 is, if we normalize it, H of 0 is
0.
Here 1. Unnormalized would be 1. So for a first order difference, H0 would be 1, and H of 1 would be here's 0. If a term is 0, we don't have to include it in the block diagram. You just remove it because I'm multiplying by 0, so I can remove that path. But for a first order difference, the input-output relationship is right. So for the negative 1. So right. So for the first order difference, it would be 1 and minus 1. For the averaging filter, unnormalized, 1 and minus 1 and 1. For the averaging filter, 1 and minus 1 for the first order difference.
So it's the only difference between
The only difference? That's right. All right, let's derive the discrete time convolution formula. And it uses system properties. And there's a few steps to get there, and then we'll look at the averaging filter again as an example. So there are a couple of, tricks, I guess, along the way. There's one trick, and the rest are properties, I suppose. So we're going to have a LTI. Well, we'll just have a. It's going to have to be an LTI system. So we have an LTI system, and we'll see that as we do the use of the properties. So this will need to be linear and time invariant. For this to work. And this is just the notation of my system. One input, one output. Input is x of n, output is y of n. So to get to the convolution formula, the first step is really where the trick is. And this is a pretty useful decomposition. So any signal can be decomposed into a sum of discrete time impulses. Right? So how do I do that? So I take x of m, whatever it happens to be. So here's x of n. And I can write this as a bunch of individual impulses that are added together. Okay, so this particular impulse is located at index -1. So it's going to, I can write this as x of -1 times a discrete time impulse at n plus 1. The index is -1. Wrong color. The origin, I can write that as, how would I write the origin?
X of 0 times delta n.
Yeah, x of 0 times delta n. Right. And so forth. So I take final, we'll just do one more, x of 1 times discrete time impulse delayed by 1 sample. So now I can write x of n as really just a weighted sum, a weighted combination of all these discrete time impulses. So when little m is 0, I have the origin. I pick off the amplitude value at the origin. Little m is 1, I pick off x of 1. Little m is -1, I pick off x of -1. And if I sum from -infinity to infinity, I represent x of n explicitly. Go ahead.
So in this situation, you're just convolving your signal with the delta function. You're not convolving it with
There's no convolution here. This is just a product.
okay.
Remember, the discrete time impulse is well behaved at the origin. Remember, the impulse, there's my discrete time impulse. Right, at the origin, it has value 1, and it has 0 value elsewhere. Right, and so forth. Right, this goes out to -infinity, and this goes out to infinity. And the ellipses are there just to show continuation, right? So it's a well-defined signal. It's a function. Every index n maps to a unique amplitude value. And so this is just a product because the impulse is either 1 or 0 in value. 1 means on and 0 means off. You can think of it that way. So again, it's an impulsive event that happens at the origin. So once I've decomposed x of n into a bunch of simpler components, I now can take advantage of system properties to finally get to the convolution result. So we're going to apply linearity, which involves both additivity and homogeneity. So the first observation is that this system is being applied to a summation. And from the additivity property, if I have a sum of signals at the input, I get a sum of their individual outputs. So I can change the order of the summation and of application of the system. The system works with respect to discrete time little n. So I interchange these two, so I swap these two for the property of additivity. then the system is being applied to x of m times the discrete time impulse at n minus m. But the system, the time for the system is little n. So anything that doesn't depend on little n is a constant. So x of m looks like a constant. So now I can use homogeneity to swap the order. And what I'm left with is the output of the system for an input that's a shifted discrete time impulse. That shifted, so what is that? Well, from time invariance, we know it's whatever the response is to the impulse delayed by m. Okay? And that is the definition. The definition of the impulse response is the response to an impulse, right? So we know that if we put an impulse into an LTI system, we can actually get the impulse response of any system. It doesn't have to be LTI. We can put an impulse in and look at what comes out. It's particularly meaningful when it's LTI. Okay. So if I put a delayed impulse in, I get a delayed output, delayed by the same amount because of this property of shift or time invariance. Right, shift invariance is another word for time invariance, also known as time invariance. And there we have it. There's our convolution formula. In this formula, we're holding x in place and flipping and sliding h about it. We can do a variable change of variables to get the other form. And this is the form that we need for filtering. So we have a preference. We want to hold h in place and flip and slide. We hold the impulse response h in place and flip and slide the input about the impulse response. All right, simple example, averaging filter, two-tap, normalized averaging filter. So again, here's our impulse response. Apply the discrete time convolution formula. There are only two values of little m that are needed to be looked at, which is little m is 0, little m is 1. Just run the convolution formula. I get h0 times x of n. That's when little m is 0. When little m is 1, I have h of 1, x of n minus 1. H of 0 is a half, h of 1 is a half. I get the familiar input-output relationship between input x and output y. And I somehow did not change my variable, so this should be an n. Okay, is this pretty good? It's okay. Okay, let's now talk about the difference between the continuous time convolution, discrete time convolution, and we'll do an animation. Okay, so continuous time convolution, if I convolve two signals x and h, I have a placeholder variable of convolution. Here I call it lambda. We're going to integrate that out. We hold one signal in place. Here I'm going to hold x of t in place and flip and slide h about x. So that, again, the flip is in. So here's the flip. And there's the slide. Okay, so I'm going to flip in lambda and slide in t. Right, so when t is 0, there's no slide, just a flip of h with respect to lambda. So for each value of time in seconds, little t, I could compute a different and possibly infinite integral to get the answer. Pretty tedious. Went through these exercises in signals and systems. And so what's more common is we break up x and h into intervals and convolve the intervals to get y. In discrete time, it's the same story, or it's a similar story. I get a placeholder variable of convolution, which is little m. So my flip here is in minus m. The slide is from the outer variable, discrete time index n. I can hold x in place and flip and slide h about x. But again, in filtering, we're going to prefer the second version, which is keep the impulse response in place and flip and slide the input about the impulse response. For each value of discrete time variable little n, we would compute a different and possibly infinite summation. Again, lots of tedious calculations, generally speaking, here. So why is this even important? Well, for an LTI system, it can be characterized uniquely by the impulse response. If I give you the impulse response, you need nothing else about the LTI system. And if you think about it, this is another reason why you need zero initial conditions. This doesn't work if your initial conditions aren't zero. I need to give you now the values of the initial conditions. Then the statement wouldn't be true. So this is a byproduct of the zero initial conditions. So we've characterized an LTI system uniquely by the impulse response. So if you know the impulse response, and I give you an input signal, you can always compute the output in the time domain by convolving the impulse response and the input. And this is what filters do in the time domain. They do convolution. They implement convolution. I don't have to tell you any more than that. Just the impulse response. So I'm going to run some demos from Johns Hopkins, or the Johns Hopkins University website. So we'll do both in continuous time and discrete time. And these are going to be Java applets for each domain in time. And so again, just one simple example that I'll do is convolving a rectangular pulse with a rectangular pulse. And we're going to use this throughout the semester. Pretty important relationship. So if I convolve two rectangular pulses of the same width, I get a triangle, and the triangle is as wide as the width of x plus the width of x plus the width of h. Now they're the same width, so the total width now becomes two times the width of the rectangular pulse being used. What's your intuition if these two pulses were of different length? What would this shape be? Trapezoid. Okay, we also need that later. Very, very important. Okay, so here is an applet from Johns Hopkins University, and I get to select some signals, or I can draw my own. So I'll start with two rectangular pulses. So I have x and h. Each is a rectangular pulse. Height 1. It's hard to see the 1 here, but it's a height of 1 in both cases. Now, to do the convolution, I hold 1 in place. Here I'm going to hold h in place, and I'm going to flip and slide x about h. And so the leading edge here is little t. That's my shift. So I'll come in from the left and shift all the way to the right to animate this. So at any point in little t, I'm going to multiply the two together. Now initially, for quite a while, the product is 0. And eventually I'll get some overlap. So we get out of the way of folks over here. So if I do the flip and slide, I get the product now gives me a rectangular pulse that gets wider with increasing t initially. And so I get complete overlap. That's going to be my maximum value of the convolution. And as I continue, I will now get overlap, but decreasing amount of overlap until there is no overlap. Okay. And the dot here down here tells me where I'm at in terms of little t based on my slide. So again, flip and slide, no overlap, I get 0. Partial overlap, I get increasing answer. Complete overlap, I get the maximum value. And then decreasing, and then 0. So that's a rectangular pulse. Now if I do two rectangular pulses of the same width. Okay, so let's do two rectangular pulses of different widths. I'll do my best hand sketch here. It'll be the sum. Yeah, it's not exactly flat. I'll try one more time. All right, it's as close as I'm going to be able to get. So we're just going to go with it. All right, so we're going to flip and slide. We're expecting something that looks like a trapezoid. It's going to be close. A little bit of error in it. There we go. As you predicted. Okay. So if we do the flip and slide again, I get initially no overlap, no overlap. I get partial overlap. And then this complete overlap, happens for a while, where blue is completely in the interval of the red, which means that the x that I'm flipping and sliding is in the extent of h, and eventually decreasing overlap. Now let's think about this in terms of a filter. So let's think about h of t now as an impulse response. And what kind of selectivity would this filter have? Rectangular pulse. The red one. The impulse response is a rectangular pulse. What's the frequency response look like? It's a shifted sync. What's the magnitude response look like? Low pass, high pass, band stop.
Low pass?
Low pass. Good job. Why is it low pass?
So you have that lobe at the...
Yeah, so the Fourier transform is a sink centered at the magnitude response is a sink centered at 0. So it's a low pass response. And you looked at this in homework 0 and homework 1. Now let's let me hand sketch a signal. Let's see. Let me get some crazy discontinuities in here. Okay, bam. Okay, good. Now I'm going to apply this. When I convolve it now, it's the effect of filtering, where the impulse response is the rectangular pulse, low-pass filter. So what's your expectation here of the output? Can it be just as crazy, or is it going to be crazy or less wiggly? I like the answer. Hard to quantify wiggly, but we're going to go with it. All right, so here it is. Flip and slide, and what do you know? It's less wiggly. All right, so a lot of these crazy corners got smoothed out, which corresponds to high-frequency information. That's low-pass filtering. All right, that's discrete time. That's continuous time. All right. Discrete time, very much the same story. Still an applet from the Johns Hopkins University.
Yes, sir.
Yep.
So, I've got the term smoothing filter before. Is that what this is?
This is a smoothing filter. You got it. And in discrete time, the smoothing filter an example of a smoothing filter would be an averaging filter. You got it. Smooths out noise and other, wigglies. Yeah, it gets rid of the wigglies. All right, so here is discrete time convolution, 2 rectangular pulses of the same duration, 4 samples each. If I do flip and slide, I'll hold x in place and flip and slide x about h. And what shape do you expect to see? It should be the same thing, a triangle. How wide will that triangle be? I got x is 4 samples in duration, h is 4 samples in duration. I hear 8. I hear 7. 7 or 8. Okay, we graduate I graduated on partial credit, and you will too, but you got to kind of go with 7 or 8 you have to pick 7 or 8, but not 7 or 8, I guess. So one gets you partial credit, one gets you full credit. Who's going to go with 8? 7. Who's going with 7? Well, okay, everyone's going with 7. It's voting anyway. So, all right, we're going to go with 7. All right. It turns out the origin is handled differently in discrete time. The origin contributes when I convolve 2 causal signals, and that origin, if you remember, doesn't in this case, right? So if I go back to 2 rectangular pulses, the origin is 0. But I look in discrete time, and because it's on an integer grid, I end up with some contribution at 0. It's meaningful. That difference causes the length to be 1 less in discrete time. So I have triangular result, triangular pulse, but the duration is 7 samples. All right, let's do, let's see, what else can we do? Something that looks like filtering. So what's the highest frequency signal I can do here?
So simple. Wherever your sample happens, you go from each one to make a
I could do, yeah, so my highest frequency is going to alternate between 1 and -1, or here I'll do 3 and -3. It's really just as good. So let me get a really high frequency tone here. Let's see, oops, no, I want you down here. All right, you go up there. Good enough. All right, so now we do the flip and slide. What do you expect?
pretty much reduced amplitude.
Yeah, reduced amplitude, because it's the highest frequency possible as a signal going through a low-pass filter. So you get some smoothing here. It's not as crazy in the alternation in the result. Okay. Any questions before we break? All right. Thank you. We'll see you on Friday.